Well, hello, my lovely chemistry students, and you know it is a great day, even when you're sick, when you get to learn chemistry. So, my sickness will not stop me from getting this video out to you so you guys aren't completely lost on the topic of how to use mole ratios in stoichiometry. And yes, the fun is just beginning. Some people really like stoichiometry, some people don't. But once you realize stoichiometry is just literally dealing with ratios of things, it can get a lot more easier to wrap your mind around. All right, so this is what we're going to be going over today. Okay, what is a mole ratio? A mole ratio is a conversion factor that relates the amounts in moles of any two substances involved in a reaction, or you can be talking about ratio of atoms within a compound. So, for example, for a compound mole ratio, H2O, the 2 indicates you have 2 moles of hydrogen for every 1 mole of oxygen in 1 mole of water. So if you were to split 1 mole of water apart, you would get 2 moles of hydrogen, 1 mole of oxygen. In a reaction, the mole ratio is referring to the stoichiometric coefficient, so the numbers before the chemical compounds or molecules. So if you are reacting hydrogen and oxygen, in this case, the stoichiometric coefficient of 2 is telling you that it takes 2 moles of hydrogen gas to react with 1 mole of oxygen gas. So you can use this when you're relating reactants to each other, products to each other, or from reactants to products. They all have mole ratios in relationship to each other. This is definitely the foundation of stoichiometry, is understanding the ratios either within a compound or between different substances in a reaction. So we're going to start out with mole ratios within compounds first because that's a little bit easier. We're going to base this on the chemical formula in order to determine like how many atoms or molecules of something are in that compound. Okay, so when you're looking at a subscript, this tells you not only like, so example, for 1 molecule of water, we have 2 hydrogen atoms covalently bonded to 1 oxygen atom. But you can expand that, since we don't usually deal with things on a just 1 molecule level, to moles. So if you think about 1 mole of water, again, there would be 2 moles of hydrogen for 1 mole of oxygen. So the subscripts in this case could represent moles. You can do this for a lot more complicated atoms like glucose, or not atoms, sorry, molecules like glucose. We have C6H12O6, so there would be 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen in 1 mole of glucose. And I know that might seem weird because you're like, well, if you add these all up, you don't get 1, you get a really big number. But I'm talking about moles differently, right? A mole is 6.02 times 10 to the 23rd atoms or molecules. So 1 mole of glucose is 6.02 times 10 to the 23rd molecules of glucose. But there are 6 times 6.02 times 10 to the 23rd carbon atoms within that 1 mole of glucose. Because remember, you can be talking about a molecule or an atom when you're talking about a mole of something. It's just a way to represent something, but it is 6.02 times 10 to the 23rd somethings, whether that be molecule, atom, formula unit, ion. You can even use it for electrons. Okay, so now let's look at calcium hydroxide here. If you have something in parentheses, you want to make sure to multiply that subscript by everything in the parentheses. So there are 2 moles of oxygen and 2 moles of hydrogen, along with 1 mole of calcium in calcium hydroxide. And we're talking about within 1 mole of that compound. So likewise, if you're looking at something like aluminum sulfate, there'd be 2 moles of aluminum, 3 moles of sulfur, and 4 times 3 is 12, so 12 moles of oxygen within 1 mole of aluminum sulfate. So why do we care about the number of moles of atoms within compounds? Well, we can use these mole ratios in order, along with dimensional analysis, to figure out other calculations like the number of atoms. So once you know the moles of atoms in a compound. If you multiply that by Avogadro's number, you can figure out, well, how many atoms are in 1 mole of that substance. Don't forget that a ionic compound or an ionic compound is not known as a molecule, but it is like one unit of that is called a formula unit rather than like a mole of a covalent substance, which is known as, the individual units are molecules. Just making sure you understand that. So if you start out with a molecular compound, right, like H2O, there's 2 moles of hydrogen per 1 mole of water. So how many hydrogen atoms are there in 1 mole of water? Well, 2 times 6.02 times 10 to the 23rd. That's all you got to do. Make sure you just multiply the number of moles by Avogadro's number to get number of atoms. Likewise, if you have the number of atoms, right, you can divide by Avogadro's number to get to the moles of that atom. And then you can divide by the subscript ratio. So instead of multiplying by 2 here, you would divide by 2 in order to figure out how many moles of the entire substance you had. So in this case, it would be water. If you had an ionic compound, again, you would multiply by the subscript ratio. So how many of those atoms are in the compound? Then you would multiply by Avogadro's number, and that would give you the number of formula units. The number of atoms within a mole of that ionic compound. If you just wanted to know the number of formula units, right, you would just look at the compound as a whole rather than individual atoms. Make sure when you're doing dimensional analysis like this, you want to arrange your conversion factor so that the unit you want is on top. Okay, so let's go through some more examples here. Okay, so again, water, very simple, easy example. That's why I use it a lot. So what if you have 0.750 moles of water? You want to figure out, well, okay, how many moles of hydrogen and how many moles of oxygen are in water? So what you would do is you can see, well, it's a 2-to-1 ratio for hydrogen, so I would just multiply that number by 2 and get 1.5 moles of hydrogen. But luckily, there's only 1 mole of oxygen per water, so that would still be 0.750 moles of oxygen. If you wanted to figure out the total number of molecules, you'd use Avogadro's number. Sometimes that's denoted by, I know it's hard to see, but N with a little subscript A in it. So you would take the moles, right? For example, oxygen, multiply it by Avogadro's number, and that is how many atoms. Why does it say molecules? I'm sorry, I'll change it. That's supposed to say atoms. There are 4.52 times 10 to the 23rd oxygen atoms. If you're looking at another more complex compound like glucose, say you have 2 moles of glucose. Well, how many oxygen atoms are in glucose? Okay, well, I know that there are 6 moles of oxygen for every 1 mole of glucose. So I'm going to multiply 2 moles of compound, which is glucose, times the ratio, the mole ratio, which is 6-to-1. I would get 12 moles of oxygen. And then simply multiply again by Avogadro's number to give me 7.23 times 10 to the 24th oxygen atoms in glucose. So here's some other examples of using mole ratios with individual compounds. You can see here for calcium hydroxide, again, 2 moles of oxygen and 2 moles of hydrogen and 1 mole of calcium in 1 mole of the substance. So if you're given a problem where it says, hey, you have 3 moles of this, how many moles of oxygen are there? Well, again, just multiply by the mole ratio, 2-to-1, so you get 6 moles of oxygen. Same thing for hydrogen, 6 moles of hydrogen. But total, how many moles are there? Well, you know that there are 5 moles of atoms total, right? 2 of oxygen, 2 of hydrogen, 1 of calcium. So 5 moles total of atoms. If you multiply that by 3, you get 15 moles of atoms. And that makes sense because oxygen and hydrogen make up 12 moles of atoms, right? But then you again have the 1 mole of calcium, but multiplying that by 3, because you have 3 moles of the compound, that's the additional 3 moles there. So you have 15 moles of atoms total in this compound. Looking at aluminum sulfate, you can do the same kind of thing. You can do different, types of problems with this, but if you are given the formula units first, so say, and the reason I say formula units is because this is an ionic compound, so the individual component is called a formula unit. You're given 1.25 times 10 to the 24th formula units. The first thing you want to do with that is, okay, well, how do I get from that to moles? Instead of multiplying by Avogadro's number, we want to divide by that in order to get moles. So we're going backwards along that pathway I showed you earlier. And dividing by Avogadro's number, we get 2.07 moles, and that's of the aluminum sulfate. If from there you want to find moles of oxygen, for instance, you can then just multiply by the mole ratio because now you have moles. You have to basically use moles to get to anything else. So when in doubt, convert to moles. So the mole ratio between oxygen and the entire compound would be a 12-to-1 ratio because remember there's 4 here, multiply it by 3 to give you 12. That will give you 24.8 moles of oxygen per mole of aluminum sulfate. You can do the same kind of thing with sulfur, but this time there's only going to be 3 sulfurs in every mole, so I'd multiply by 3 to get the moles of sulfur. And then if I wanted to go from there and say, okay, well, hey, and that many moles of sulfur, how many atoms are there? Again, just multiply by Avogadro's number. So you can go kind of any way you want to along that flow chart I showed you to get where you need to be. But usually you have to go through moles first. So here's some extra practice problems for you to look at. You can take some time and do those on your own. Okay, so next, now that we know how to use mole ratios within a compound, we have to know how to use mole ratios in a chemical reaction using stoichiometric coefficients. In order to do this, you have to have a balanced chemical equation. If your equation is not balanced, and then you will not have the right mole ratios that is represented by the stoichiometric coefficients. So in this case, if you're looking at a reaction, you're saying 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. So it's a 2 to 1 to 2 ratio. So you can use stoichiometric coefficients of any balanced chemical reaction to get from the moles of one substance to the moles of another substance. So for example here, we have a 2 to 1 ratio between hydrogen and oxygen. So if you have a reaction and you use 4 moles of hydrogen, okay, well, how much oxygen do you need? You need half that. You would need 2 moles of oxygen. And so these mole ratios help you determine how much reactant you need to make a reaction occur, or maybe how much product you will make. Or if you're given how much product is made, you can back calculate how much reactant you would need. Oh, also one more thing. Don't forget that if there is no coefficient, assume a coefficient of 1 for these balanced chemical equations. So kind of the way I think about this is after you have the balanced chemical equation, you want to figure out, okay, what information am I given and what do I want to get to? And from that, you know what conversion factors to use. So for example, if you're given the mass of a reactant and you want to figure out the moles of a product you can make from that, what do? When in doubt, convert to moles. So if you're given the mass of a reactant, just divide by the molar mass, and that will give you the moles of that reactant. From there, you can use mole ratios in any way you need to get to the substance you need. So B and A just represent, different substances in a reaction. It's like A reacts with B to make C. So if you wanted to figure out maybe how many moles of B were required, you'd multiply by the mole ratio between B to A. If you wanted to figure out how much product you could form, you'd multiply the mole ratio of C to A. And then once you have the moles of whatever you're looking for, you can always convert it back to grams by multiplying by molar mass if the problem requires that. Common mistakes to avoid here that I have seen: using subscripts instead of coefficients for the mole ratios. That is not the case when you're dealing with balanced chemical equations. You can only use subscripts as mole ratios if you're talking about one compound or molecule by itself, not a reaction as a whole. The skipping the convert to mole step, okay? I have seen people skip step 2 and just go, or sorry, not step 2, skip step 3 and just go right to 4. So they're using grams and then they just go ahead and multiply by the mole ratio. You can't do that because you need to have moles of something to cancel out with moles of in the denominator. So remember, the units have to be the same to cancel according to dimensional analysis. It's easier if you set up the equation with your units so you know what cancels and what you need to have in order to make the math make sense. So let's go over some calculations here. Um, so again, you can go from moles of one substance to another using the stoichiometric coefficients and the mole ratio. If you're not directly given moles in the problem, if you're given particles or atoms, again, you use Avogadro's number, you would divide by that to get to moles. If you're given mass of something, you would use the molar mass. So you would divide by molar mass in order to get to moles. If you want to ever go from moles to mass, you would multiply by molar mass. And this chart is given in your data booklet, so you don't have to have this memorized. Okay, let's look at an example here. So the combustion of methane requires 1 mole of methane, 2 moles of oxygen gas to make 1 mole of carbon dioxide and 2 moles of water. So what are you given in this problem? 16 grams of methane. Okay, if you have grams, what do you want to do first? Convert to moles. The molar mass of methane is 16.04 grams per mole, so I would divide by that to get moles of methane. And the problem wants me to find the grams of carbon dioxide produced as the product. So once I have moles of methane, the only way to get from methane to carbon dioxide is use that mole ratio. This is an easy example because they are in a 1-to-1 ratio. So for every 1 mole of methane, you will produce 1 mole of carbon dioxide. So if you have this 0.998 moles of methane in the problem that you calculated, you will also produce 0.998 moles of carbon dioxide. Last step to get to grams, just multiply by the molar mass of carbon dioxide because remember, this is moles of carbon dioxide, so we want the molar mass of carbon dioxide, which is 44.01. And so therefore, from 16 grams of methane, we would produce 43.9 grams of carbon dioxide. Here's another example with water. If you are if you are looking for the mass of water produced rather than carbon dioxide, you could do the same type of thing. Instead of using our 1-to-1 ratio, though, we produce 2 moles of water for every 1 mole of methane. So we'd multiply by 2 at this step in order to get moles of water, and then multiply by Avogadro's number to get the however many molecules of water that we produce. So from here, if this problem, for example, was asking us for molecules, instead of multiplying by the molar mass, we would multiply by Avogadro's number. So it just depends on what the problem is asking for as to what you're going to do in the last step. Here's just some more examples here. I have the synthesis of sodium chloride from sodium and chlorine gas. If you are given the moles of chlorine and you want to figure out how much salt you can produce. Okay, so at this stage of our stoichiometry learning, we're going to assume that if we are given the mass or moles, whatever, of one reactant, the other one, we just have an excess of that. So the chlorine is going to be, the reaction is going to be dependent upon how much chlorine there is because that's what's going to run out first. So we're just going to make that assumption for now. So if it ever gives you, for right now, the mass or moles of a reactant, just assume the other one, we have enough of it. All right, so we have our 3 moles of chlorine. We're going to try to get to salt. We don't have to do any math to get to moles because the problem already gives us moles. So it's really easy because then we can just use the mole ratio, and it's a 2-to-1 ratio. So we multiply by 2 to get 6 moles of sodium chloride we would produce. Then to convert to mass, we just multiply by the molar mass in order to get our final answer, which is 351 grams. You can look at the same kind of thing over here. We have the decomposition of potassium chlorate to make potassium chloride and oxygen gas. If we're given grams of it, we want to figure out how much oxygen we can produce. This one is a little bit more steps, right? We have grams, so we have to get to moles first. Going from grams to moles, we divide by the molar mass. Then once we have the moles of our reactant, we have to use our mole ratio. In this case, it's not a clean ratio, right? Before we've been using like a 2-to-1 or a 1-to-1 ratio. This time it's a 3-to-2 ratio. So don't be scared of that. You just have to multiply by 3 and then divide by 2 to get moles of oxygen gas produced. Then multiply by the molar mass. And remember, this oxygen is diatomic. Don't forget to multiply the 16 by 2 to get 32. And we would produce 9.60 grams of oxygen. So here's just a summary slide. I guess the key thing I would say is always travel through moles. You cannot get from one substance to another without using the mole ratio. That is the only bridge between two different quantities. Within compounds, don't forget, subscripts can refer to the moles, but in chemical reactions, we're looking at the coefficients to determine mole ratios. And then I have some extra practice problems here for you guys to try at different levels. Let me know if you have any questions, and I hope you have a fabulous day. Bye-bye.